these definitions of accuracy, precision, and error become really important, especially on paper 3. In the first part of paper 3 especially. You know, in the first part it's called section A, where you've got all these questions about the prescribed experiments. So in this, those definitions, especially about error, become really important. And I like this Star Wars reference here about, you know, only the Imperial Stormtroopers are so precise. I mean, these definitions themselves aren't actually that difficult, but you need to know them really well in order to actually succeed in your exams. So let's look at the word accurate. The word accurate, what we mean is a small systematic error. And I'm going to explain the word systematic error as well. But it means they're close to the real value, the quote-unquote real value. So what do I mean by that? Let me see if I can do, just paste something here. Yeah, good. So let's just say you're doing, I mean, this is the old trope. Everybody uses archery as an example, but it actually works. So let's just say I'm doing a whole bunch of archery here. And I want to see something that's accurate. So a small systematic error. That means they're close to the real value. So in this case right here, let's see something then that is, let's see, I'll try to draw on it here. So let me say something right here that is, let's just say like this here. So really, really close to the real value. So this one right here, for example, if I shot a whole bunch of arrows right here, do you notice they're close to the real value? In other words, in this case, they're close to the center or whatever they're supposed to be. So they're pretty close to this right here. So we could say these are accurate. Now I'm just going to show you the contrast just so we can actually compare these words. We've got the word after that called precise. And there what it means, there's a small random error. And what I mean by that, they're close to each other. So what I'm going to try to do again is paste something here. Yeah, there we go. Do another one. So I'll show you something else then that's small random error. Do you know, by the way, I'm going to define them a little bit clearer too. I'm just going to start with this. So let's do something then as a small random error. Let's say I shot a whole bunch of them, but they're all really close to each other. Maybe they're all right here. Whole bunch of them. They all hit right over here. In this case here, you could say these are here are precise. Now these words accurate and precise, something can be accurate and precise, it can be accurate and not precise, and so on. So now take a look at this. So again, precise means close to each other. They're grouped close together. They don't necessarily have to be where they need to be. So in this case, these are precise, but you could say they're not accurate. Do you know how you can say that? Because if they are accurate, they'd also be close to the center. In this case here, they're accurate because they're close to the center. And it depends on if you want to consider this close to each other or not. Then, you know, it's a bit of a dodgy definition. In this case right here, you could say, but not precise, you know, because you could say that, well, they're not totally close to each other. Again, it just depends what you mean by close, doesn't it? So maybe we'll go into these definitions a little bit more detail. So systematic error. What do we mean by a systematic error? It means that everything is off by a certain amount. So in this example back here, you know, I said there's a small systematic error. In other words, things weren't off by very much. Whereas over here, can you see you're trying to shoot the center of the target, but instead you're way off all the time. So in this case right here, everything is off by a certain amount. And what I mean by that is that, you know, more experiments, they won't help. You probably need to recalibrate your experiment. And an example of that could be, let's see here if I can get a little pen going here. So let's just say you're doing an example of something like Hooke's law, if you know that one, where you have a whole bunch of data points here. So let's just say I have some things here. I'll draw some error bars here. So I have one here and I have another one here. Let's just say, so I'm just drawing myself some data points with some error bars. Like this right here. And if I draw a line of best fit through this bad boy, let's see here what I would get. Let's see if I can draw that. That would be something like this, right? Not exactly, but something like that. So if you take a look at this, you can say, all right, so there's my points, there's my uncertainty, so my error bars on those points. But if you know about Hooke's law, at 0, this would be like a spring. You know, if you've got a spring and you attach some weights to it or some masses to it, as the spring extends, you know, that'll be the force on it. So the force on it, as it increases, the extension will increase. So in this case, that's what this would be a graph of. And I hope it makes sense that at 0 displacement, it should be for 0 force. So in other words, this thing, you're expecting it to pass through 0, 0, but it's not. So in this case right here, can you see that right here? Whoa, I didn't mean to do that. Don't mess it up there, Mitch. There we go, like this. This one right here, do you see we're off by that same amount? We're always off. So we're off by this amount. So this means we have a systematic error. In other words, every value you did is off. It's sort of messed up by the same amount. So if you just repeated it a lot, it wouldn't change. You'd still just be off by the same amount. You need to recalibrate. You need to maybe remeasure things in order to fix it. By contrast, a random error, this is where the data points don't match the others. So maybe I'll do an example of that here. So I'll just show you some data points here. So let's just say I'm drawing some data points. So here's a data point, let's just say, and here's another data point here. I'm just drawing some data points with some error bars here. And then I have a point that's over here. Let's just say something like this. I'm drawing it poorly, of course. But do you see that? I mean, if I drew a whole bunch of data points like this here, you'd see that, you know, most of them match, and most of them seem to follow this dotted line, or this line, right? Most of them seem to match. But there's this one weirdo point here. You know, there's one that just doesn't really fit. That is your random error. That one right there is the one that's messing everything up. You probably made a mistake. Probably. Or just something weird happened. In this case, more experiments will help. Do you see that? Because if you do this, more experiments are going to help because you're going to reduce your random errors. So for systematic errors, more experiments don't help. You need to recalibrate. But if you have random errors, more experiments will actually help. And then I have an example. Oh no, wait, not an example yet. Really important, actually. Yeah, I'm really glad I checked this. Line of best fit. Oh my God, this is so important. Does it need to be a straight line? In other words, if you're looking at something like, you know, you got some sort of graph. It doesn't matter what it's a graph of, right? It could be, I don't know, potential difference versus the current, let's just say. And you would expect to be a straight line, maybe, but I don't know. Maybe you get data points that do, you know, something like this right here. And maybe then, oh, I don't know, maybe it does something different. Maybe it's something like this. So the question is, does it have to be a straight line? And maybe I have another point maybe up here like this right here. Well, not quite like this, but maybe way up here like this. There we go. So the question is, does it have to be a straight line? No. So that's the answer for sure. It's no. It just has to fit through the error bars. That's the key thing. In other words, if I was trying to draw a straight line through this right here to make it pass through all the error bars, I probably can't. Because at the bottom right down here, all the way up to the top right here, I probably can't make it pass through all the error bars. So if that's the case, you can actually state it's not a linear fit. You know, this right here, for example, is something that's going to be a curve. That might be my line of best fit. So lines of best fit do not have to be straight. They just have to pass. This is the key thing. They need to pass through the error bars. That is the key stipulation here. This is what has to happen. They gotta pass through the error bars. As long as they do, it can be whatever curve you need. Now I have an example. So let's just say we're given an archery target and you're given this right here. And you might say, do you have, because before I define these as accurate versus precise, let's see, this was, for example, a question very, very recently on an exam on a paper 1. This for SL and HL. And the question had been asking, you know, what kind of uncertainties do you have here? So try to think about, do you have random uncertainties? Do you have systematic? Do you have neither? Or do you have both? Think carefully about them now. So instead of accurate and precise, you got to think about them as random versus systematic. First of all, I can say, so here's the answer. The answer is, let's see. First of all, we have systematic errors. Do you know why we have those? That's because they're off from the center. Do you notice? Like they're not at the center. They're off a little bit, aren't they? So we have systematic. How about random? Do we have random errors here? I would say yes, we have random errors because they're also not so close to each other. Do you notice they're a little bit spread out? Had they been all tightly grouped, then you could say there's very little random errors. So in this case, I would say, yeah, you have plenty of systematic errors and you have plenty of random errors as well.